Alright, this is Mr. Gillum, and today we're going to start proving triangles are congruent using another postulate, the side angle side postulate. But before we get into that, we need to talk more about the side postulate. And what it says, if you remember, is that if all the sides are congruent of two triangles, then the triangles are congruent, because the angles must also match. So before we do anything, though, I want to talk about the distance between points, and we're going to look at some triangles on a coordinate plane here. And we're going to determine if they're congruent or not. Now, on this specific example, I'll give you a chance to go ahead and plot these points. Triangle ABC has these coordinates, and I'd like you to go ahead and plot those on your own paper. And EFG has these coordinates. Okay. And now let's just look at it and kind of just eyeball it here. These triangles do not look congruent. Okay, they don't. They don't look congruent. And so let's just remember our congruent statement here is triangle ABC is congruent to EFG. All right, let's just keep that in mind. Using the side postulate, that means that the length between A and B should be equal to the length between E and F. So what we're going to do is we're going to use the distance formula. And right now it's just more of a practice with substitution than anything. It's just an algebraic practice, but we're going to get into why the distance formula is what it is here in just a second. So as I look between these 2 points, I have my A coordinate and my B coordinate. A is 1, 1, and B is 0, 3. And I need to find the distance between point A to point B, as well as the point E to point F. And point E is 1, negative 1, and point F is 2, negative 5. I'm going to use the distance formula on 2 different occasions here. And it shouldn't take me long to disprove that these are not congruent triangles based on AB comparing to EF. If they are congruent according to side, all their sides will be congruent according to this congruent statement. So I just started with the AB part, comparing it to the EF part. The distance between point A and point B can be found by using this formula for the distance. Okay, so that's what I'm going to do right here. I'm going to say the distance between A and B is the square root of x2 minus x1. So in this case, these are 2 pairs, order pairs. And to keep them separate, we use something called a subscript. So these are both x and y pairs. But to know which x and which y I'm talking about, we're going to call A the x1, y1, and B the second x and y, or x2, y2. And so when I'm plugging in my numbers here, that's where they're coming from. X2 is 0 minus 1, x1, and 3 minus 1. Okay, so the distance can be found by computing this, this little formula here. The distance of AB is the square root of negative 1 squared plus 2 squared. So in this case, the distance AB is equal to the square root of 1 plus 4, which is the square root of 5. And there's no need to put a decimal. It should work out. We'll know whether they're equal or not, depending on whether the distance between E and F is congruent to the square root of 5. So now let's take a look at, so let's just make sure I got these guys right there, and we'll go ahead and do EF over here on the side. So we have, once again, the distance formula, and this time we're doing EF, so we keep track of it. And our little formula here. So once again, we have these 2 points. They're both x and y, but to keep them straight, we give them little subscripts. So this is the first x and the first y, the second x and the second y. I'm not squaring those values. They're just little subscripts. And so I'm doing x2 minus x1, as stated in the formula. So in this case, 2 minus 1, and y2 minus y1, negative 5 minus negative 1. Be careful with these negatives. You do need the minus and the negative sign, so if parentheses helps you, that's fine. That'd be best. So the distance between E and F equals the square root of 1 squared plus negative 5 minus negative 1 is negative 4 squared. All right, and then finally, the distance between E and F in this case will equal the square root of 1 plus 16. So in this case, the distance is the square root of 17. And if I'm trying to prove the side-side-side postulate and prove that these triangles are congruent, obviously these triangles will not be congruent because in my congruent statement it says AB should equal EF. And in this case, my AB value, my distance, my segment length is 5, root 5, and my distance for my E to F is root 17. So these triangles are not congruent. All right, so that has been determined. I find the distance, and that represents the side length of each one. And according to my congruent statement, they should be equal, and they are not. Therefore, through side, 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 there's a contradiction, so they are not congruent triangles. Now, the distance formula is nice and everything, but it's even nicer if you actually understand where it's coming from. And so what we're going to do is we're going to derive the distance formula, and we're going to see what's happening and why it works. Okay, using prior knowledge. So the Pythagorean theorem is going to be huge in this. So I'm just going to pick two subjective points, and I'm going to label them. Let's just use this guy right here, and we'll just use this guy right here. And since they're just points in space, it doesn't really matter. I know I put them on a coordinate plane, but they're just points. We'll call this guy the first point, x1, y1, the first point, and the second point, x2, y2. All right, so just two subjective points. And now the thing is, for the distance formula is I want to know that what I'm looking for is the distance from here to here in a straight line. All right, so there's some strategy I can employ here without even using the distance formula. So the clever mathematicians, they noticed, okay, well, I don't know how far that is. And so what I'm going to use is knowledge of Pythagorean theorem and right triangles to help me get there. So what they said was, all right, well, let's just do a little dashed line and just turn this into a right triangle here. Okay, it's a perfect right triangle. Now, I know relationships between the right triangles, legs and hypotenuse. Leg squared plus leg squared equals the hypotenuse squared. And so what we can do here is we can say, all right, well, let's just assign these points, these subjective points, it doesn't matter where they are, values. In this case, we're at 2, 2, so we'll call him 2, 2. And in this case, we're at 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 5, 8. All right, and so if I wanted to find the horizontal distance, it wouldn't be that bad. I could take 5 minus the 2, and I would find that this is 3. Or I could do the 8 minus the 2, and I could find that this is 6. And so that's really everything. That's the whole thing. That's where the distance formula comes from. Because as you see, what I have here is whatever the subjective point's value is, in this case it happens to be 8, and this coordinate 5, if I subtract where I'm already at, these distances, I can use the Pythagorean theorem. So in my right triangle, this distance is represented by the x2 value minus the x1 value. And this distance is represented by the y2 value minus the y1 value. Okay, Pythagoras, his theorem says, well, if I have a right triangle, then I know that the leg squared plus the leg squared should equal the hypotenuse squared. Or in this case, any two subjective points, one leg squared plus the other leg squared must equal the distance squared that we're looking for. This is the distance we're looking for. All right. And so through a little bit of work, he just said, oh, well, let's just find the square root of all that. And so I know the distance must be the square root of, between any 2 points, is the square root of x2 minus x1 squared minus, plus y2 minus y1 squared. And that's the distance formula. So there you go. That's where it comes from. So that might just happen to show up as a quiz question or a test question. It might just say something like derive the distance formula. In fact, I know it will. So you'll be responsible to explain to me in diagram how the distance formula is related to the Pythagorean theorem. Okay, so you will need all these little subscripts. You won't need the actual numbers here because that's not, these are just generic numbers. It doesn't matter. I could put the points anywhere. It could be a point right here and a point right here. The distance formula still works. But you will need to be able to explain the relationship between the distance formula and the Pythagorean theorem. All right, now let's get to what we're trying to get to here. Now we're going to learn about the side angle side postulate. And it says if two sides of a triangle and an included angle are congruent, then to two sides of another triangle and its included angle, then the triangles are congruent. So as you can see, here's a diagram. These triangles are congruent through the side angle side postulate. I have a side and a side, and the included angle is the one that is the most important. That's really important because on your worksheet I noticed there's a few that they give you that two sides are congruent, but they don't tell you that the included angle is congruent. No, it has to be two sides and their included angle, meaning the angle that they form between them. All right, that's the side angle side postulate. And so now we have another tool in our tool belt here to solve these proofs that we've been doing. Okay, so instead of having to solve for all three segment lengths, and all three angle lengths and show that those are all congruent, we went to side, 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 showing that just the three sides of each triangle are congruent. And now we're going to add the side angle side, where we need a side, an angle, and a side, but the angle must be included between the sides. Okay, so let's just take a look here. Looking at this problem here, it says the scaffolding for stage lighting shown appears to be made up of congruent triangles. If segment WZ is congruent to YX and WX is parallel to ZY, write a two-column proof to prove that triangle WXZ is congruent to triangle YZX. Now, I believe there's a typo in this problem, but I want you to see it with me here. As I know we're just learning side angle side, but we do know the side angle side should be two sides and its included angle. So the problem with this problem, the issue with the problem is that it gives us that WZ is congruent. WZ is congruent to XY. It doesn't say they're parallel, it just says they're congruent. And it says WX and ZY or YZ are parallel as well. It says write a two-column proof to prove that angle WXZ is congruent to triangle YZX. Now, the problem I have with this proof is this. I have a side that I know is congruent to a side, and I have another side here that I know must be congruent to the other side. But the problem is, if these are the two sides I'm talking about, I need to somehow guarantee that this angle is equal to this angle, or is congruent to that angle. And I think I'm going to have some issues doing that because I don't know the relationship between this guy, this side, and this side. And so I can't really say it's an alternate interior because the two transversals aren't guaranteed to be the exact same angle. And so what we're going to do is we're going to change this problem a little bit because it's going to be impossible to prove with the given information. But we can prove that they are congruent triangles if they gave us the following information. Instead of telling us WZ is congruent to YX, let's change it. Let's change it to WX. So we're going to change this guy. WX is congruent to ZY. And now I think we'll have a little better luck proving that the two triangles are congruent. However, I do not recommend that you change the problems in your book repeatedly to make them easier for yourself. I just think that this one had a little typo, that's all. So, okay, so let's take a look here and we saw it. So now we have new given information. I'm saying this side and this side are congruent, and I'm going to also say that this guy is parallel to this guy. All right, and so now as I'm going through my proof, it should be workable where I can actually use the side angle side postulate to help my prove that these are congruent triangles. So we're going to start out with some given information here, and like I said, we don't want WZ is congruent to YX. We want to actually put WX is congruent to ZY. Okay, or it should actually be, I should actually write that the other way. It should be YZ. Okay, and it also tells us that that the lines are parallel. So, like I said, not recommended to change your problem. Just in this case, we need to. Now, if I know that, then I know also that with this transversal right here, that these angles must be congruent. The alternate interior angles theorem tells us this, and it's something that we talked about last chapter. Okay, so it tells me that alternate interior angles are congruent. That's the alternate interior angle theorem. So now we're well on our way. We have a side, we have an angle, and now the reason we changed the given information is because our last side has to actually be including the angle. So this is the last side that the two triangles share together. And so through the reflexive property, I know that that ZX is the same as XZ. And then finally, the triangles are congruent then through side, angle, side. I have a side, an angle included, and a side, an angle included, and a side. Okay, so then